Welcome back to another fascinating journey through time. Today, we're standing at the base of structures so magnificent, so impossibly ambitious, that ancient peoples themselves believed only gods could have built them. The Great Pyramid of Giza towers above us, its 2.3 million stone blocks defying gravity and time itself. Across the ancient world, stone monuments pierce the sky. Temple complexes sprawl across landscapes, and engineering marvels carry water across continents. These aren't just buildings. They're impossible dreams made real by human hands. How did they do it? This question has haunted us for centuries. Without modern machinery, without computers, without steel or concrete, ancient engineers accomplished feats that would challenge us even today. They moved stones weighing as much as jumbo jets. They calculated angles with breathtaking precision. They organized thousands of workers into coordinated symphonies of human effort. And they did it all with bronze tools, wooden sledges, and hemp ropes. Some have claimed these wonders must be the work of lost advanced civilizations or even extraterrestrial visitors. But the truth is far more inspiring. These monuments represent humanity at its most ingenious, most determined, most collaborative. Every massive stone placed, every perfect angle calculated, every soaring arch constructed tells us something profound about human capability and ambition. We're about to embark on a journey across continents and millennia. We'll walk the ramps of pyramid construction sites, feel the spray of Roman aqueducts, and witness the raising of massive temple columns. We'll meet the brilliant minds who solved engineering problems that would baffle many today, and the countless workers whose sweat and skill transformed ambitious dreams into enduring stone reality. The question isn't whether ancient peoples could build these wonders. The question is how they became the most remarkable engineers in human history. Chapter 1. The mathematics of the Great Pyramid. The desert sun beats down mercilessly on the Giza Plateau in 2560 BCE. Before you stretches a site that shouldn't exist. Workers swarm across a growing mountain of limestone blocks, each stone cut with impossible precision, each course laid with mathematical perfection. This is the Great Pyramid of Khufu in its birth, and you're witnessing the greatest engineering project the world has ever seen. The architect Hemiunu stands at the base, papyrus scrolls in hand, surveying his life's work. He faces a problem that would terrify modern engineers. He must organize 100,000 workers to place 2.3 million stone blocks, some weighing up to 80 tons, into a structure that will rise 481 feet into the sky. Every block must fit with gaps no thicker than a knife blade. The base must be perfectly level across 13 acres. The sides must align precisely with true north, south, east, and west. And all four triangular faces must meet at a single point in the sky with mathematical perfection. No pressure. But here's what makes this truly impossible. Hemiunu doesn't have blueprints as we understand them. He doesn't have calculating machines or computer models. He has copper tools, wooden measuring rods, plumb bobs, and human genius. Yet somehow, the Great Pyramid will be built with an accuracy that staggers modern surveyors. The base is leveled to within just 1 inch across 756 feet. The sides align to the cardinal directions within 3/60th of a single degree. This isn't just impressive, it's nearly incomprehensible. The mathematics required boggle the mind. Ancient Egyptian architects understand geometry with sophisticated precision. They know the Pythagorean theorem 1,000 years before Pythagoras is born. They calculate the pyramid's slope using a sect system, measuring horizontal distance against vertical rise with remarkable accuracy. The chosen angle, roughly 51.8 degrees, isn't random. It creates a pyramid whose height relates to its base perimeter in almost exactly the same ratio that a circle-east radius relates to its circumference. Some scholars believe this golden ratio is intentional, demonstrating knowledge of pi to several decimal places. But knowing the math and executing it across 13 acres of desert are vastly different challenges. The first task is leveling the foundation. Workers flood the base area with water from the Nile, creating a perfectly level surface. They cut channels into the bedrock and fill them with water, then mark the water level on the rock walls. After the water drains, they chisel away everything above the marks, creating a foundation level to within inches across the entire site. It's brilliant in its simplicity, using water's natural tendency to seek its own level as a massive liquid level tool. Next comes the astronomical alignment. On the night of the autumn equinox, priests and astronomers work throughout the darkness. They observe the rising and setting points of specific stars, particularly those in Ursa Major that never dip below the horizon. Using a simple tool called a merkhet, essentially a plumb line and sighting rod, they establish true north with astonishing precision. They mark the alignment with great care, because every measurement throughout the entire construction will reference these initial markings. The surveying work is meticulous. Workers stretch ropes across the site, creating a grid system. They use gypsum powder to mark lines on the level bedrock. Teams of specialized measurers constantly check and recheck distances using standardized measuring rods. These rods, made of wood or copper, are carefully maintained and regularly compared against master rods kept in temples. Every significant measurement is checked multiple times by different teams. The stakes are too high for error. As the first course of massive limestone blocks is laid, the precision becomes evident. Each block is carved from quarries with bronze and copper tools, pounded with stone hammers and shaped with wooden wedges driven into cracks. The blocks don't just sit together, they interlock. The ancient masons understand that weight alone won't create a stable structure. They shape each block so its weight distributes properly to the blocks below, creating a self-supporting structure that will last millennia. The interior chambers present even greater challenges. The king's chamber, buried deep within the pyramid's mass, must support hundreds of thousands of tons of stone above it. The architects design an ingenious system of relieving chambers, 5 separate void spaces above the main chamber, each topped with massive granite beams weighing up to 80 tons. These distribute the enormous weight away from the burial chamber, ensuring it won't be crushed. Above these relieving chambers, they create a pointed roof, directing stress to the sides rather than downward. It's structural engineering of breathtaking sophistication. The grand gallery, an ascending passage with a corbelled ceiling rising 28 feet high, demonstrates advanced understanding of architectural principles. Each stone course projects slightly beyond the one below, creating a self-supporting arch. The ancient architects understand that if the angle is correct, the structure will hold itself up through compression alone. The craftsmanship is so precise that modern visitors can barely fit a playing card between the stones. Hemiunu's mathematical genius extends to logistics as well. He calculates that if 100,000 workers each place one block every 3 minutes during daylight hours for 20 years, they'll complete the structure on schedule. He organizes the workforce into teams, each with specific tasks. Stone cutters in the quarries, transporters moving blocks, builders placing them, and measurers constantly checking alignment. It's a human machine of incredible complexity, all coordinated through ancient management techniques we barely understand. The mathematics of ramp construction alone would fill modern textbooks. To raise blocks up the growing pyramid, workers build ramps. But how? A straight ramp to the top would need to be longer than the pyramid itself and require more material than the pyramid. Instead, they likely use spiral ramps wrapping around the structure, or internal ramps built into the structure itself. Recent scans revealing void spaces within the pyramid support this theory. The ramp must maintain a manageable slope, probably around 10%, requiring constant recalculation as the pyramid grows higher. Every calculation, Every measurement, every astronomical observation serves one purpose: achieving immortality through perfection. The pharaoh's eternal resting place cannot be flawed. The structure must stand forever, a mountain made by human hands, a stairway to the heavens. And so Hemiunu and his teams work with obsessive precision, knowing that their mathematical perfection will determine whether they're remembered as master builders or forgotten failures. The Great Pyramid succeeds beyond imagination. For over 3,800 years, it stands as the tallest human-made structure on Earth. Modern engineers, studying it with laser scanners and computer analysis, remain astounded by its precision. The ancient Egyptians didn't just build a tomb. They created a testament to human mathematical genius, a demonstration that with enough knowledge, coordination, and sheer determination, humans can achieve the impossible. Every perfect angle, every precisely cut stone, every mathematical calculation proves that our ancestors were not primitive. They were pioneers of sciences we're still perfecting today. Chapter 2. Moving mountains without machines. The Nile floods have receded, leaving behind rich silt and, more importantly for our story, a highway of mud. Teams of workers gather at the limestone quarries of Tura, just across the river from Giza. Before them lies today's challenge: a limestone block weighing 15 tons. That's the weight of 3 full-grown elephants. It must be moved 12 miles to the pyramid site using nothing but rope, wood, water, and human muscle. The quarrymaster Seneb surveys his crew of 200 workers. These aren't slaves, as popular myth suggests. Archaeological evidence reveals that pyramid builders are skilled workers who receive payment in bread, beer, and meat. They live in purpose-built workers' villages with bakeries, breweries, and even medical facilities. Building the pyramid is considered a sacred duty, and these men take pride in their work. Their graffiti, found throughout the pyramid, names their work gangs with titles like Friends of Khufu and Drunkards of Menkaure. Seneb's first task is extracting the stone from the quarry face. Workers have spent days creating channels around the block using copper tools and stone pounders. Now comes the critical moment. They drive wooden wedges into carefully placed holes along the stone's base. Workers pour water over the wedges. As the wood swells, it generates enormous force, slowly cracking the stone free from the bedrock. It's a technique requiring patience and precision. Rush it, and the block fractures. Time it right, and the stone separates cleanly. The block breaks free with a deep grinding sound. Workers cheer, but the real work is just beginning. They must now lever this massive stone onto a wooden sledge. Teams work wooden beams under the stone's edges, using the mechanical advantage of levers to lift one side at a time. They slide wooden rollers underneath, inch by inch, until the stone rests on a sturdy sledge made of timber beams. The sledge distributes the weight and provides a smooth surface for dragging. Here's where ancient engineering brilliance truly shines. Recent experimental archaeology has revealed a technique that seems almost too simple to work. Workers carry large water jugs to the sledge's path. They pour water onto the sand in front of the sledge, saturating it thoroughly. This seems counterintuitive. Wouldn't wet sand make pulling harder? But physics proves otherwise. The water reduces friction by nearly 50%. Dry sand particles bunch up in front of the sledge, creating enormous resistance. Wet sand compacts, creating a firm, slippery surface. Wall paintings from ancient Egypt clearly show a worker standing on the front of sledges, pouring water onto the path. For centuries, scholars thought this was religious ceremony. It's actually sophisticated engineering. 200 workers take their positions along ropes attached to the sledge. A foreman begins a rhythmic chant, and the team pulls in unison. The massive stone begins to move. Slowly, incredibly slowly, but it moves. The workers strain, their feet digging into the sand, and the sledge slides forward. Inch by inch, foot by foot, the impossible journey begins. The workers understand rhythm and coordination are everything. They pull together on the foreman's count, maximizing their collective force while minimizing wasted effort. But moving the stone over level ground is only the beginning. The path to the pyramid includes ascending the desert plateau. Workers have prepared long, gradual ramps, essentially artificial hills of packed earth and stone. The sledge must be hauled upward against gravity. To help, workers have driven vertical stakes into the ramp at intervals. Ropes loop around these stakes, creating what engineers call a mechanical advantage through changed direction of force. Some scholars believe they also use counterweights, baskets of stones that descend as the sledge ascends, helping to haul it upward. The journey takes days. Workers spell each other in shifts, keeping the stone moving whenever possible. When they rest, they tell stories, sing songs, and share bread and beer brought by support crews. The logistics of feeding and housing these workers are staggering. Archaeologists have found evidence of massive bakeries capable of producing thousands of loaves daily. Cattle bones show that workers consume significant amounts of meat, a luxury for ancient common people. This isn't just construction, it's a massive economic enterprise engaging the entire society. As the stone approaches the pyramid site, even greater challenges await. The block must be raised up the growing structure. The exact method remains debated, but evidence points to several ingenious solutions working together. Long ramps spiral around the pyramid's exterior, or internal ramps wind through the structure itself. Recent scanning technology has revealed void spaces within the pyramid that might be remains of internal ramps. As each level is completed, workers adjust or rebuild ramps for the next level. For especially heavy stones, like the granite beams weighing up to 80 tons, workers employ even more sophisticated techniques. They build temporary embankments alongside the pyramid, creating artificial hills that allow them to drag stones to the required height. After construction, they dismantle these embankments, removing evidence of their existence. It's why modern scholars have struggled to understand the building process. The ancient engineers were so efficient they removed most traces of their methods when they cleaned up the site. Lifting stones the final distance onto each course requires precision tools. Workers use wooden rockers, essentially curved beams placed under the stone that allow it to be rocked back and forth, gaining height with each movement. They use levers with fulcrums placed strategically to lift one edge at a time. They pack stones and wood under the lifted edge, then move to lift the other side. Gradually, in a carefully orchestrated dance of levers and packing materials, they raise the massive block to the level of the current course. The final positioning demands extraordinary skill. The block must slide into its precise position, fitting against neighboring blocks with gaps of less than half a millimeter. Workers use wooden rollers under the stone, allowing fine adjustments. They tap wedges to shift the stone fraction by fraction. Master masons check the placement constantly with plumb bobs and level instruments. When the stone settles into its perfect position, workers cheer. One more block placed. Only 2,299,999 to go. The human effort required staggers the imagination. Calculations suggest that if workers move 10 blocks per day, working every day for 20 years, they'll need to move 37 blocks daily to complete the pyramid on schedule during the peak construction years. This requires unprecedented organization and logistics. Quarries must produce stones continuously. Transport teams must work around the clock. Builders must place blocks faster than seems humanly possible. And yet, the pyramid rises, defying limitations we imagine for ancient peoples. Modern experiments have validated ancient methods. Teams using only ancient technology have successfully moved multi-ton stones significant distances. In 2014, a team of 50 people moved a 2-ton stone using ancient techniques, confirming that the methods work. Scaled up to hundreds or thousands of workers, moving the pyramid's blocks becomes physically possible, if extraordinarily difficult. The ancient engineers understand something profound about physics and human organization. They know that massive weights can be moved with relatively simple tools if you understand mechanical advantage, friction, and coordinated effort. They develop sophisticated logistics to keep materials, tools, and workers in constant supply. They create management systems to coordinate thousands of people working simultaneously on different tasks. They're not just moving stones. They're inventing project management, supply chain logistics, and large-scale engineering coordination. Every block placed represents human triumph over physical limitations. Without engines, without electricity, without modern materials, ancient workers move mountains. The sledges, ropes, and rollers are simple tools. The engineering principles behind them are timeless. The real miracle isn't any single technique. It's the combination of practical physics knowledge, brilliant organization, and sheer human determination. The pyramids stand today not because aliens built them, but because humans refused to accept the impossible. Stone by stone, they proved that with enough knowledge and effort, there are no limits to what we can achieve. Chapter 3. Stone Cutting Secrets. The sun has barely risen over the Aswan quarries when the sound of hammering begins. A team of stonemasons surrounds a massive granite outcrop, their copper chisels glinting in the early light. This particular section of granite has been chosen for the king's chamber in the Great Pyramid, where the pharaoh will rest eternally. The granite must be cut from solid bedrock, shaped with precision, polished to perfection, and transported hundreds of miles, all with technology that seems impossibly primitive to modern eyes. Master Mason Kenti examines the granite face, running his hands over the stone, feeling for flaws invisible to untrained eyes. Granite is among the hardest stones on Earth, far harder than the copper and bronze tools available to ancient Egyptians. This presents a puzzle that has confounded scholars for decades. How do you cut something harder than your tools? The answer reveals ancient engineering brilliance that modern science is only now fully appreciating. The first tool isn't copper or bronze at all. It's dolerite, a stone even harder than granite. Workers have gathered smooth dolerite balls, each weighing several pounds, from specific quarries where this stone outcrops. These balls become hammers, pounders that workers swing repeatedly against the granite surface. It's brutally hard work. Each impact removes only tiny chips of granite, but thousands of impacts, delivered by hundreds of workers over days and weeks, gradually pulverize the granite surface. Workers create shallow channels around the area they want to separate from the bedrock. The channels grow deeper, fraction of an inch by fraction of an inch. The rhythmic pounding creates a sound that echoes across the quarry. Workers develop calluses on their hands that eventually become thick as leather. They work in rotating shifts, staying fresh to deliver maximum impact with each blow. The technique requires more than strength. Workers must strike at precise angles to create even channels. They must avoid fracturing the stone with poorly aimed blows. It's skilled labor requiring years of training. Kenti introduces another technique for creating straight cuts. Workers drill a series of holes into the granite using bow drills fitted with stone or copper tips. The drill bit is embedded with quartz sand, harder than granite, which does the actual cutting as the drill spins. Workers add water to create a cutting slurry. They bear down on the drill with considerable force while pulling the bow back and forth rapidly. It's exhausting work. A single hole might take hours to drill just a few inches deep. Once workers create a line of holes along the intended cut, they drive wooden wedges into each hole. Then they pour water over the wedges. As the wood absorbs water, it swells with tremendous force. The expansion is slow but inexorable, generating pressure of several tons per square inch. If workers have placed the wedges correctly and drilled the holes at the right depth and spacing, the granite cracks along the desired line. The stone doesn't shatter. It separates cleanly. It's a technique requiring deep understanding of stone properties and enormous patience. For some cuts, particularly interior work requiring smooth surfaces, workers use copper saws. These saws are surprisingly large, some up to 9 feet long. The copper itself is too soft to cut granite, but workers add quartz sand as an abrasive. They work the saw back and forth, applying constant pressure. The sand particles, harder than granite, grind through the stone. Workers must continuously add fresh sand and water to maintain cutting efficiency. A single cut might take weeks of continuous work. Archaeological evidence reveals even more sophisticated techniques. Copper tube drills, hollow cylinders of copper rotated with tremendous pressure, create circular holes in granite. Workers find the telltale spiral grooves left by these drills in ancient quarries and unfinished stones. The drills reach depths of several feet, maintaining remarkable straightness. Recent experiments have successfully replicated this technique, though it requires enormous physical effort and constant replenishment of quartz sand abrasive. The precision achieved with these seemingly primitive tools astounds modern craftspeople. Granite blocks in the king's chamber fit together with gaps of just 0.5 millimeter. The surfaces are flat to within thousandths of an inch. The corners are true right angles. When modern stonemasons attempt to replicate this precision using ancient tools, they're humbled by how difficult it is. The ancient craftspeople aren't just workers. They're master artisans who've spent lifetimes perfecting their skills. Polishing presents yet another challenge. To create the mirror-smooth surfaces found on granite sarcophagi and temple columns, workers use progressively finer abrasives. They begin with coarse quartz sand, grinding the stone's surface smooth. They progress to finer sands, then to powdered materials. The final polish uses powdered red ochre or even powdered feldspar. Workers rub these materials onto the stone surface using flat grinding stones, working in circular motions for hours. The result is a surface so smooth that it reflects light like glass. The scale of stone cutting operations beggars belief. The Great Pyramid alone requires cutting and shaping 2.3 million blocks. For the 20-year construction timeline, quarries must produce and finish roughly 300 blocks daily. This demands an industrial-scale operation with hundreds of workers spread across multiple quarries, all producing stones to precise specifications. The logistics of tool manufacture alone are staggering. Copper tools wear down rapidly against stone. Workers must constantly sharpen or replace them. This requires extensive copper mining, smelting, and metalworking operations to support the quarries. Ancient engineers developed specialized tools for specific tasks. They create copper chisels in various profiles for different types of cuts. They manufacture standardized measuring tools to ensure consistency across work teams. They develop wooden templates that workers use to check angles and dimensions. The sophistication of their toolkit rivals that of modern stonemasons, just using different materials. Quality control is rigorous. Overseers constantly inspect work, rejecting blocks with flaws or imprecise dimensions. Rejected stones are set aside, sometimes repurposed for less critical uses, but never placed in the pyramid structure if they don't meet standards. This explains why archaeologists find unfinished stones in quarries. If a stone cracked during extraction or showed flaws during shaping, workers abandoned it and started fresh. The standards are uncompromising. Transport of shaped granite from Aswan to Giza, a distance of about 500 miles, represents another engineering triumph. Workers load granite blocks onto barges during the annual Nile flood when water levels are highest. The barges themselves are marvels, constructed specifically to carry immense weights. They float the granite downstream, using the river's current to do most of the work. When they reach Giza, they offload the stones and transport them to the construction site. The ancient stonecutters understand something fundamental about their craft. Stone isn't merely cut, it's persuaded. They work with the stone's natural grain and internal structure. They identify weaknesses where the stone wants to separate. They understand that patient, consistent effort succeeds where brute force fails. They develop an intuitive feel for stone properties that takes years to acquire. The relationship between mason and stone is almost spiritual. They're not just cutting rocks. They're revealing the perfect shape hidden within the rough block. Modern engineers, studying ancient stonework under microscopes and with advanced imaging, continue discovering evidence of techniques we don't fully understand. Some cuts show characteristics suggesting tools or methods we haven't identified. The precision achieved in some pieces seems to exceed what should be possible with known ancient technology. This doesn't mean ancient aliens or lost advanced civilizations. It means ancient engineers were more capable than we've credited. They developed techniques refined over centuries, passing knowledge from master to apprentice across generations. Every perfectly cut block, every polished surface, every precise angle testifies to ancient humanity's refusal to be limited by available technology. They didn't have modern tools, so they became better craftspeople. They couldn't rely on machines, so they developed unmatched skill. The stone-cutting secrets of ancient engineers aren't really secrets at all. They're lessons in patience, precision, skill, and the determination to achieve perfection regardless of limitations. Every stroke of the chisel, every swing of the stone hammer, every hour spent polishing reminds us that human hands, guided by human intelligence and refined by human practice, can create miracles. Chapter 4. The Geometry of Gods. The morning star Venus rises over the city of Ur in ancient Mesopotamia, 2100 BCE. High priest and architect Hemiunu stands atop a partially completed ziggurat, gazing at the heavens with instruments that seem deceptively simple. A plumb line hangs motionless in the still air. Measuring rods marked with precise intervals lie at his feet. Clay tablets covered in cuneiform calculations rest nearby. Before him stretches the foundation of what will become a bridge between earth and heaven, a structure that must align perfectly with celestial mechanics the ancient Mesopotamians have studied for generations. The ziggurat rising beneath Hemiunu's feet represents more than religious devotion. It's a monumental exercise in geometry, astronomy, and architectural planning. Unlike Egyptian pyramids built as tombs, ziggurats serve as temples, artificial mountains where priests can ascend closer to the gods. But this spiritual purpose demands extraordinary precision. The structure must align with celestial events. Its proportions must reflect sacred mathematical relationships. Every dimension carries symbolic meaning while also serving structural purposes. Ancient Mesopotamian geometry is sophisticated beyond what most imagine. Cuneiform tablets reveal that these engineers understand the Pythagorean theorem more than 1,000 years before Pythagoras. They calculate square roots to remarkable accuracy. They understand the relationship between a circle's circumference and diameter. They use base 60 mathematics, a system so effective we still use it for measuring time and angles today. Every 60 seconds in a minute, every 60 minutes in an hour, every 360 degrees in a circle traces back to ancient Mesopotamian mathematical brilliance. Hemiunu's tablets contain architectural plans of stunning complexity. The ziggurat's base must be a perfect rectangle. Its corners must align with cardinal directions. Each terrace must rise at carefully calculated angles, and the entire structure must ascend in precise proportions. The architect uses a unit of measurement called a cubit, standardized across the Mesopotamian world. But he doesn't just measure. He calculates volume from material estimates, designs drainage systems to prevent water damage, and plans stairways that will remain stable under the weight of thousands of pilgrims. The construction begins with astronomical observations. On the night of the spring equinox, priests track the rising and setting sun. marking its positions with wooden stakes. Over following nights, they observe specific stars, particularly those that never set below the horizon. Using shadow-casting gnomons, vertical poles that cast shadows, they determine true north with remarkable precision. These observations aren't casual. Teams of trained astronomers work for weeks, cross-checking results, ensuring accuracy that will determine the orientation of a structure meant to last millennia. Foundation layout requires geometric precision that challenges modern understanding. Workers establish the corners using what later generations will call the 3-4-5 triangle method. If you create a triangle with sides measuring 3 units, 4 units, and 5 units, the angle opposite the longest side is always a perfect right angle. Mesopotamian engineers understand this principle intimately. They stretch ropes marked at these intervals, creating perfect right angles at each corner. They verify diagonal measurements, ensuring the foundation is not just rectangular, but perfectly rectangular. The ziggurat rises in distinct terraces, each level smaller than the one below, creating a step pyramid effect. This design is both aesthetic and structural. The setbacks reduce weight on lower levels, while creating a visually impressive ascending structure. But the geometry must be exact. If one terrace is misaligned even slightly, the error compounds with each subsequent level, resulting in a structurally unsound building or one whose peak doesn't align properly with celestial observations. Hemiunu constantly checks vertical alignment using plumb bobs suspended from wooden frames. The plumb line hangs true under gravity, showing workers whether walls rise perfectly vertical. Material calculations demonstrate advanced mathematical understanding. Hemiunu must estimate how many mud bricks the structure requires. A simple rectangular building is easy to calculate, but a ziggurat with multiple terraces, stairways, internal chambers, and decorative features requires complex volumetric calculations. The architect breaks the structure into geometric components, calculating each section separately, then summing the totals. He must also account for brick losses during transport and construction, estimate mortar requirements, and plan for brick-making operations that must produce millions of standardized bricks over years of construction. Temple builders across ancient Mesopotamia share knowledge through travelers, traders, and sometimes forced relocation of skilled workers when cities conquer one another. This creates a tradition of architectural excellence that spans generations. Young apprentices study under master builders for decades, learning not just construction techniques but the mathematical and astronomical knowledge underlying them. They memorize calculation methods, learn to read the stars, and develop geometric intuition that becomes almost instinctual. The Mesopotamians understand that architecture is frozen mathematics. Every angle, every proportion, every dimension expresses numerical relationships. They favor certain ratios that they consider sacred or aesthetically perfect. The ratio of width to length in temple chambers often follows patterns found in nature, proportions that create spaces feeling balanced and harmonious to human perception. Modern studies of these proportions reveal they often approximate what later mathematicians will call the golden ratio, approximately 1.618, a proportion appearing throughout nature and considered aesthetically ideal. Water management presents particular geometric challenges. Mesopotamia's climate includes intense seasonal rains. Without proper drainage, water accumulates in structures, weakening mud brick and causing collapse. Ancient engineers design elaborate drainage systems, calculating slopes that allow water to flow off terraces without eroding the structure. They create channels and gutters with precisely calculated gradients, steep enough for effective drainage, but not so steep that water flows with erosive force. They waterproof certain surfaces with bitumen, a naturally occurring asphalt available in Mesopotamia. Interior spaces demonstrate understanding of acoustics and light. Temple chambers must accommodate ritual chanting and musical instruments. The geometry of rooms affects sound reflection and amplification. Ancient architects adjust ceiling heights and wall angles to create acoustic properties appropriate for religious ceremonies. They position openings to channel natural light into specific areas at specific times, often aligning with religious calendars, so sunlight illuminates sacred statues or altars on important festivals. Stairway design requires careful geometric planning. Steps must ascend at comfortable angles for humans, typically around 30 to 35 degrees. Each step must be identical in height and depth, preventing stumbling. The Mesopotamians used standardized measurements for steps, creating consistency across different buildings. But stairways on ziggurats serve dual purposes. They're functional passages and symbolic ascents toward heaven. Their geometry must be both practical and spiritually significant. The ancient builders understand structural load distribution through geometric principles. Mud brick is strong in compression, but weak in tension. Walls must be thick enough to support weight above them without crushing. As structures rise higher, walls must become thicker, but not so thick that they waste materials and space. Engineers calculate optimal wall thickness using rules developed through centuries of experience and occasional catastrophic failures. They learn from collapsed structures, understanding that angles and proportions that fail teach as surely as those that succeed. Decorative elements incorporate geometric patterns that aren't merely ornamental. The Mesopotamians developed complex tile patterns, mosaic designs, and brick arrangements, creating visual interest while reinforcing structural integrity. They understand that certain geometric patterns distribute stress more effectively than uniform arrangements. Decorative elements often serve structural purposes invisible to casual observers. Modern mathematicians, analyzing ancient Mesopotamian structures, continue discovering geometric sophistication we barely imagined possible. Computer modeling reveals that many temples incorporate complex mathematical relationships in their proportions. Some structures align not just with cardinal directions, but with specific celestial events, requiring understanding of astronomy and mathematics that challenges assumptions about ancient capabilities. The geometry of temple builders represents accumulated knowledge spanning thousands of years. Each generation refines techniques, corrects errors, and pushes boundaries. The great ziggurats standing across Mesopotamia don't emerge from primitive peoples stumbling toward understanding. They rise from a sophisticated civilization with advanced mathematics, precise astronomical knowledge, and geometric understanding that matches and sometimes exceeds what we teach in schools today. Every carefully calculated angle, every precisely proportioned chamber, every astronomically aligned axis proves that ancient engineers didn't just build temples. They built mathematical demonstrations, geometric proof that human reason can comprehend the universe as underlying order and reflected in enduring stone and brick. Chapter 5. Roman concrete. The harbor of Caesarea Maritima bustles with activity. In 22 BCE, ships from across the Mediterranean unload cargo while construction crews work in the shallow waters, building something unprecedented. Emperor Herod has commissioned architect and engineer Lucius Vitruvius to create an artificial harbor, complete with massive breakwaters protecting ships from storms. The challenge seems impossible. Stone breakwaters in previous harbors have collapsed under wave action. The forces involved are immense, pounding relentlessly year after year until stone crumbles and structures fail. Vitruvius possesses a secret weapon that will revolutionize construction throughout the ancient world. Roman concrete. Not the concrete we know today, but something potentially superior. A building material that will allow Romans to construct wonders that still stand 2,000 years later, some in better condition than modern structures that are decades old. As workers mix volcanic ash with lime and seawater, they're creating a material that will prove more durable than anything humanity has invented since. The formula seems almost magical. Romans combined volcanic ash, specifically pozzolana from deposits near Mount Vesuvius, with quicklime, water, and aggregate materials like rocks or broken pottery. The mixture is poured into wooden forms where it hardens into artificial stone stronger than many natural stones. But Roman concrete is more than just strong. It's revolutionary because it allows Romans to create shapes impossible with traditional stone construction. Arches, domes, vaults, and complex curved surfaces become possible. Massive structures can rise quickly without requiring enormous quantities of precisely cut stone. The science behind Roman concrete is fascinating and, remarkably, not fully understood until modern researchers analyze it with advanced technology in the 21st century. The volcanic ash contains aluminum silicates and calcium oxides that create chemical reactions when mixed with lime and water. These reactions continue for years, even decades after the concrete is poured, constantly strengthening the material. In seawater, like the harbor Vitruvius is building, the concrete actually becomes stronger over time as seawater reacts with the volcanic materials, creating mineral crystals that fill microscopic cracks and reinforce the structure. Vitruvius oversees construction of massive wooden formwork in the harbor. Workers build enormous frames underwater, a task requiring sophisticated engineering to withstand wave action while construction proceeds. They use cofferdams, watertight enclosed retrie, continue use that allow workers to build in relatively dry conditions below water level. Inside these temporary structures, they pour the revolutionary concrete mixture. The concrete sets underwater, a property that amazes even experienced builders. Traditional mortar dissolves in water. Roman concrete hardens in it, creating permanent structures in environments previously impossible to build in. The breakwaters at Caesarea stretch nearly half a mile into the Mediterranean, creating a harbor capable of accommodating hundreds of ships. The concrete structures withstand wave forces that have destroyed previous attempts at harbor construction. 2,000 years later, archaeologists studying the underwater ruins discover something astounding. The concrete has not just survived, it has actually strengthened over the centuries. Modern concrete in seawater typically begins deteriorating within 50 years. Roman concrete has lasted 40 times longer and shows no signs of significant degradation. The secret lies in the specific volcanic ash the Romans use and the chemical reactions it undergoes. Modern scientists analyzing samples under electron microscopes discover rare mineral crystals growing within the concrete. Crystals that form through reactions between the volcanic materials and seawater. These crystals, including a rare mineral called aluminum tobermorite, create an incredibly durable matrix that actually becomes stronger as it ages. It's a self-healing concrete that modern engineers are now trying to replicate. Rome itself showcases concrete's architectural possibilities. The Pantheon, completed in 126 CE under Emperor Hadrian, features the largest unreinforced concrete dome ever built. The dome spans 142 feet in diameter and reaches the same height from floor to oculus, creating a perfect hemisphere. For over 1,800 years, it remains the world's largest concrete dome. Even today, with steel reinforcement and modern materials, few buildings match its scale and ambition. The Pantheon's construction demonstrates sophisticated engineering understanding. The concrete mixture varies throughout the dome, with heavier aggregate materials at the base where compression forces are greatest, and progressively lighter materials toward the top. Near the oculus, the 30-foot opening at the dome's apex, the concrete contains pumice, an extremely light volcanic rock. This reduces weight where the dome is structurally most vulnerable. The dome's interior features coffers, recessed panels that reduce weight while adding visual interest. Each design choice serves both structural and aesthetic purposes. The dome's geometry is crucial to its stability. The perfect hemisphere distributes forces evenly around its circumference. The thick walls at the base contain 7 niches that reduce weight while creating spaces for statues. Hidden within the walls are brick arches that channel forces downward to the foundation. The oculus serves multiple purposes. It reduces weight at the dome's crown, eliminates potentially problematic apex construction, provides natural lighting, and creates a symbolic connection between the temple and the heavens. Rain entering through the oculus drains through precisely calculated floor slopes and underground drainage channels. Roman engineers understand the concrete's strength lies in its compression resistance. Like stone, it handles downward and inward forces well but cracks under tension. They design structures to keep concrete under compression, using arches and domes that naturally redirect forces into compression. The barrel vaults spanning Roman bathhouses, aqueduct channels, and basilicas all exploit concrete's compressive strength while minimizing tension forces that would cause cracking. The Colosseum, Rome's legendary amphitheater, showcases concrete construction on an unprecedented scale. Begun in 70 CE, the structure rises 4 stories and accommodates 50,000 spectators. While the exterior facade features cut stone, the interior structure is primarily concrete. Massive concrete foundations support the weight of stone seating and walls. Concrete vaults create corridors, stairways, and the complex underground hypogeum where gladiators' animals await their appearances. The structure must support not just static weight but dynamic loads from thousands of people moving, jumping, and reacting to spectacles in the arena. Roman concrete technology spreads throughout the empire, enabling rapid construction of infrastructure that binds far-flung territories together. Aqueducts carrying water across valleys use concrete in foundations and channels. Roads feature concrete layers beneath stone paving. Harbor facilities from Britain to Egypt utilize concrete to create permanent structures in challenging marine environments. Military fortifications incorporate concrete in foundations and walls. Bathhouses, temples, basilicas, markets, and warehouses all benefit from concrete's versatility and durability. The material enables architectural innovation impossible with stone alone. Romans create large open interior spaces by spanning them with concrete vaults and domes. Traditional stone construction requires numerous interior columns to support weight, limiting space and sightlines. Concrete vaults allow spacious interiors with minimal interior supports. The Basilica of Maecenas, with its massive concrete barrel vaults, creates interior spaces that seem impossibly large for ancient technology. The central nave spans 83 feet, covered by vaults reaching 115 feet high. Standing inside feels like being in a covered stadium. Quality control in concrete production is crucial. Romans developed standardized methods for mixing and pouring concrete. They understand that proper proportions of volcanic ash, lime, and aggregate determine final strength. They know that concrete must cure properly, maintaining moisture for extended periods to achieve full strength. They test materials, checking volcanic ash quality and ensuring lime is properly burned. Workers mix concrete in precise proportions, measuring materials carefully to maintain consistency. The aggregate materials Romans add to concrete vary based on intended use and local availability. For massive foundations, they incorporate large rocks, creating cyclopean concrete that combines immense strength with economy. For vaults and domes, they use lighter materials like broken pottery or lightweight volcanic rocks. For facing concrete that will be visible, they mix in fine materials, creating smoother surfaces. This understanding of material science is remarkably sophisticated, demonstrating that Romans don't just stumble upon concrete through accident, but develop it through systematic experimentation and refinement. Roman builders also understand concrete's limitations. Fresh concrete is heavy and fluid, exerting tremendous pressure on formwork. They design robust wooden forms capable of supporting concrete weight until it sets. They build elaborate scaffolding to support forms for vaults and domes. Workers must remove forms carefully after concrete hardens sufficiently. timing this crucial step to prevent collapse while not leaving forms in place unnecessarily long. The formwork for the Pantheon's dome alone requires timber from thousands of trees, creating a wooden hemisphere that must support millions of pounds of wet concrete. Concrete's economic advantages drive its widespread adoption. Cutting stone requires highly skilled masons working for months to shape blocks for a single structure. Concrete requires less skilled labor mixing and pouring materials. While specialist knowledge about proportions and formwork is essential, the actual construction work can be performed by less expensive workers. This allows Rome to build on a scale impossible with traditional stone construction. The speed of concrete construction also matters. Structures rise in months rather than years, crucial for an expanding empire needing infrastructure quickly. The Romans also developed facing techniques to beautify concrete structures. They create brick facing, arranging bricks in decorative patterns that cover concrete cores. They apply marble veneer to concrete walls, creating stunning visual effects more economically than solid marble construction. They develop stucco treatments that can be painted or carved, transforming plain concrete into decorated surfaces. The Pantheon's interior, for instance, features marble facing, coffers that were originally gilded, and decorative elements that disguise the concrete structure beneath. Modern engineers studying Roman concrete continue making discoveries. Analysis reveals that Romans have different concrete formulas for different applications. Seawater concrete differs from concrete for land structures. Concrete for foundations contains different materials than concrete for vaults. This specialization demonstrates sophisticated understanding of material science and engineering principles. Recent research attempts to recreate Roman concrete recipes, hoping to develop modern materials with similar durability. Some researchers believe Roman concrete could help address modern concerns about sustainable building materials, as it requires less energy to produce than modern Portland cement and lasts much longer. The eventual loss of Roman concrete technology after the empire's fall represents a tragic setback for civilization. Medieval builders lacked the knowledge to recreate Roman concrete's properties. They use inferior mortar that deteriorate relatively quickly. Not until the 18th century do European builders develop cements approaching Roman concrete's capabilities. The 19th century invention of Portland cement creates a material stronger initially than Roman concrete, but less durable over time. Only now are researchers rediscovering principles Roman engineers understood 2,000 years ago. Every Roman structure still standing today, from the Pantheon to aqueduct fragments scattered across former empire territories, testifies to concrete's revolutionary impact. The material allows Romans to build faster, bigger, and more durably than any previous civilization. It enables architectural forms that define Western architecture for millennia afterward. Domes, vaults, and arches become signature elements of Christian churches, Islamic mosques, and government buildings worldwide, all tracing ancestry to Roman concrete construction. The material isn't just a building technique. It's a foundation for architectural ambition that shapes human environments for 2,000 years and counting. Every modern concrete structure, from skyscrapers to bridges, owes an intellectual debt to Roman engineers who mixed volcanic ash with lime and created eternity. Chapter 6. Water flow to uphill. The Roman engineer Sextus Julius Frontinus stands at the source of a mountain spring in 97 CE, 50 miles from Rome. Water bubbles from the hillside, clear and cold, flowing at what Frontinus estimates to be several thousand cubic feet per minute. His task seems impossible. Capture this water and deliver it to Rome, crossing valleys, passing through mountains, maintaining steady flow over terrain that rises and falls dramatically. Romans demand abundant water for their bathhouses, fountains, public toilets, and private homes. The city's existing aqueducts struggle to meet demand from a population exceeding 1 million. Frontinus must build a new aqueduct, a structure that will carry water with gravity alone, without pumps or machinery, across 50 miles of challenging landscape. The engineering challenge begins with surveying. Frontinus needs to map every foot of terrain between the spring and Rome, measuring elevations with extraordinary precision. The aqueduct must descend continuously from source to destination. If any section rises higher than the section before it, water won't flow. Even a small error in surveying could doom the project. Roman surveyors use a chorobates, a wooden instrument about 20 feet long with a groove on top that can be filled with water. Since water naturally finds its level, the water-filled groove creates a perfect horizontal reference. By sighting along the groove, surveyors determine whether terrain slopes upward or downward. They work systematically across the entire route, taking measurements every few hundred feet, recording data on wax tablets. The calculations reveal a problem. The spring sits only slightly higher than Rome. Given the distance involved, Frontinus needs a gradient of just inches per mile to maintain flow without creating excessive velocity that would erode the channel. Too steep, and water flows too fast, damaging the aqueduct. Too shallow, and flow becomes sluggish, unable to deliver required volume. The ideal gradient is approximately 1 foot of drop for every 1,000 feet of horizontal distance, or about a 0.2% slope. Maintaining this precise gradient across 50 miles requires surveying accuracy that challenges even modern instruments. Where valleys cross the route, Frontinus must decide whether to bridge them or detour around them. Bridging requires constructing massive arcades, multi-tiered arch structures carrying the water channel hundreds of feet above valley floors. The famous Pont du Gard in southern France, built slightly earlier, showcases this approach. Its 3 tiers of arches rise 160 feet above the Garden River, carrying water across a valley nearly 1,000 feet wide. The engineering is breathtaking. Each arch must support tremendous weight while allowing the structure flexibility to withstand settling and earthquakes. The Romans developed sophisticated understanding of arch geometry, knowing that properly shaped arches channel forces into compression along the arch curve, allowing relatively slender structures to support enormous loads. For Frontinus's new aqueduct, some valleys are too wide or deep for practical bridging. Instead, he uses siphons, one of ancient engineering's most impressive achievements. A siphon involves bringing the water channel down one valley side, across the valley floor through sealed pipes, and up the opposite side. This seems to defy logic. How can water flow uphill? The answer lies in pressure physics. Water in the descending pipe gains pressure as it drops. This pressure forces water up the ascending pipe on the far side. As long as the ascending pipe doesn't rise higher than the water source, the siphon maintains flow. Roman inverted siphons use lead or stone pipes capable of withstanding tremendous internal pressure. At the valley bottom, pressure can reach several atmospheres. The lead pipes must be thick, and joints must be absolutely watertight. Romans developed sophisticated lead working techniques, casting or hammering lead sheets into pipes, sealing joints with molten lead. For extra safety, they sometimes encase lead pipes in concrete. The engineering calculations for siphons are complex. Romans must account for friction losses, determine required pipe diameter to maintain flow, and ensure structural integrity under pressure. Where mountains block the route, Frontinus has 2 choices: tunnel through them or route the aqueduct around them. Tunneling is extraordinarily difficult with ancient technology. Workers dig with picks and hammers, removing rock inch by inch. They use fire setting when dealing with hard rock, heating the rock face with fires then dousing it with water. The thermal shock fractures the rock, making it easier to excavate. But tunneling is dangerous. Collapses kill workers. Ventilation becomes critical in long tunnels. Surveying inside mountains requires different techniques than surface surveying. Roman tunnel engineers develop ingenious solutions. When tunneling through mountains, they sometimes work from both sides simultaneously, meeting in the middle. This requires precise surveying to ensure the tunnels align. They sink vertical shafts from the mountain surface to the tunnel level at intervals, providing ventilation, removing excavated material, and creating multiple work faces to speed construction. Some Roman aqueduct tunnels stretch for miles through mountains, representing years of dangerous work. The tunnel must maintain the precise gradient required for water flow while traversing unpredictable underground geology. The water channel itself demonstrates sophisticated hydraulic engineering. Most aqueducts use covered channels rather than open ones. The covering prevents evaporation, keeps debris out of the water, and prevents contamination. The channel cross-section is carefully calculated. Too narrow, and flow is insufficient. Too wide, and construction costs become excessive. Romans standardized channel designs, with typical channels measuring about 3 feet wide and 5 feet high, adequate for maintenance access. Workers can enter channels to clean them and repair leaks. Channel construction uses concrete or cut stone fitted precisely. The channel bottom and sides must be waterproof. Romans lined channels with a special waterproof concrete called opus signinum, made with crushed pottery that contains silicates, improving water resistance. They apply multiple layers, compacting each thoroughly. Some channels feature additional waterproofing with lead sheets or thick mortar coatings. Attention to detail is obsessive. Even small leaks waste precious water over the aqueduct's length. The aqueduct must handle thermal expansion and contraction. Temperature changes cause stone and concrete to expand and contract slightly. Over a 50-mile length, this amounts to significant movement. Romans design expansion joints at intervals, allowing sections to move independently without cracking. They understand that rigidly connected sections would crack under thermal stress. This understanding of material science is remarkably sophisticated. Flow regulation requires careful engineering. Where the aqueduct gradient becomes steeper, water accelerates, potentially eroding the channel or creating turbulent flow. Romans install cascade structures, step sections, where water drops in controlled stages, dissipating energy. Where multiple aqueducts converge, they build distribution tanks, large settling basins that allow sediment to drop out while regulating flow to different destinations. These tanks include sophisticated valve systems controlling water distribution across the city. Maintenance is ongoing. Minerals in water gradually deposit on channel walls, reducing flow capacity. Workers periodically enter channels to chisel away mineral deposits. Some Roman aqueducts accumulate deposits several inches thick over centuries, testament to consistent water chemistry and long service life. The aqueducts also suffer earthquake damage, require repairs from settling, and need replacement of eroded sections. Romans established permanent maintenance crews, specialists who spend careers keeping water flowing. The Aqua Marcia, one of Rome's major aqueducts completed in 140 BCE, demonstrates the scale of these projects. It stretches 58 miles from source to city, mostly underground to protect it from military threats and weather. At the city approach, it rises on arcades, delivering water to a castellum, a distribution facility. From there, lead pipes carry water throughout the city. The aqueduct delivers roughly 47 million gallons daily, an extraordinary volume. Construction requires a decade and employs thousands of workers. The investment is enormous, but Romans consider it essential to civilization. Aqueduct engineering spreads throughout the Roman Empire. Cities across Europe, North Africa, and the Middle East receive water through Roman-built aqueducts. Some remain functional today, 2,000 years later. The Segovia Aqueduct in Spain still carries water. Sections of Roman aqueducts throughout Europe are incorporated into modern water systems. This longevity testifies to construction quality and engineering excellence. The social impact of reliable water systems transforms Roman life. Public bathhouses become central to Roman culture, impossible without abundant water. Public fountains provide free water access. Flush toilets in public facilities and wealthy homes improve sanitation. Water flowing in fountains throughout cities becomes a symbol of Roman power and civilization. The sound of flowing water in Rome's streets is such a constant that visitors from water-poor regions consider it miraculous. Frontinus himself writes a technical treatise, De Aqueductu, describing Rome's water system in detail. It's one of the few surviving ancient technical manuals, providing invaluable insights into Roman engineering practices. Frontinus documents each aqueduct's capacity, route, and condition. He describes illegal water theft, a persistent problem where people tap aqueduct pipes without authorization. He explains maintenance procedures and the administrative system managing water distribution. His work reveals that aqueduct engineering isn't just civil engineering, but also involves complex administration, law enforcement, and public policy. The mathematical sophistication underlying aqueduct engineering is considerable. Engineers must calculate volumes, flow rates, pressures, and structural loads. They use geometric principles to design arches and determine siphon dimensions. They apply hydraulic principles, understanding how water behaves under various conditions. This knowledge, accumulated over generations, represents one of humanity's great engineering achievements. Modern hydraulic engineers studying Roman aqueducts remain impressed by their sophistication. Computer modeling confirms that Roman designs are near optimal for their purposes. The gradients chosen maximize flow while minimizing construction costs. The arch designs efficiently support loads using minimal materials. The siphon calculations correctly account for pressure and flow dynamics. Roman engineers, working without computers or advanced mathematics, achieve results that match or exceed what modern engineers would design using sophisticated tools. Every fountain in Rome, every bathhouse, every public toilet, every private home with running water depends on the aqueducts. Without them, Rome, as the ancient world knows it, cannot exist. The aqueducts represent more than engineering achievement. They represent civilization itself, the human ability to reshape environments to human needs. Water flowing through Roman aqueducts flows uphill through mountains, not because nature allows it, but because human intelligence insists upon it. The aqueducts stand as monuments to the principle that natural obstacles exist to be overcome, that human ingenuity combined with determination can make water flow where it has never flowed before, bringing life and civilization to places that would otherwise remain dry and barren. Chapter 7. The Megalithic Mystery. The massive stone monoliths stand in silent rows across the Salisbury Plain in southern England, their weathered surfaces bearing witness to 45 centuries of wind, rain, and human wonder. Stonehenge, perhaps the world's most famous prehistoric monument, presents a puzzle that has fascinated and frustrated archaeologists for generations. How did Neolithic people, working around 2500 BCE without wheels, without draft animals, without metal tools stronger than copper, transport stones weighing up to 40 tons from quarries over 150 miles away? The question becomes even more perplexing when we learn that these builders shaped the stones with precision, raised them upright, and capped them with massive lintels, creating trilithons that have stood for millennia. The sarsen stones, the massive sandstone blocks forming Stonehenge's outer circle, and the iconic trilithons, come from the Marlborough Downs, about 20 miles north of the monument site. 20 miles may not seem far, but imagine moving a stone weighing 40 tons without modern machinery. That's equivalent to 6 full-grown elephants. The smaller bluestones, though weighing only 2 to 4 tons each, present an even greater mystery. Geological analysis proves they originate from the Preseli Hills in Wales, over 150 miles away. Some scholars suggest glaciers transported the bluestones closer to Stonehenge during ice ages, but evidence increasingly supports human transportation across this staggering distance. Recent archaeological discoveries illuminate how these prehistoric engineers accomplished their impossible task. Excavations reveal ancient trackways, wooden paths laid across marshland that would have been impassable for heavy loads without artificial surfaces. These trackways use split logs laid side by side, creating roads capable of supporting sledges carrying massive stones. The wood choice matters. Oak and ash, common in Neolithic Britain, provide strength and durability. The trackways follow the driest routes possible, avoiding steep slopes and the wettest ground. Experimental archaeology provides crucial insights. In 2016, a team of volunteers successfully moved a 2-ton concrete block using only Neolithic technology. They placed the stone on a wooden sledge, essentially a platform with runners like a sled. The ground in front was prepared with logs laid perpendicular to the direction of travel, creating a rolling road. As the sledge moved forward over the logs, workers at the rear collected logs the sledge had passed over and carried them to the front, continuously maintaining the rolling road. About 24 people could move the 2-ton block this way at roughly 1 mile per hour over level ground. Scaling this up to Stonehenge's 40-ton seismic reveals the magnitude of the undertaking. Moving the largest stones would require at least 500 people pulling together. The ropes themselves present an engineering challenge. Neolithic people make rope from plant fibers, particularly flax and hemp, twisted into cordage strong enough to support tremendous loads. Creating ropes capable of hauling 40 tons requires hundreds of hours of rope making by skilled craftspeople. The ropes must be thick enough to handle the load without breaking, but flexible enough to be worked by human hands. The route from the Marlborough Downs to Stonehenge crosses several significant hills. Hauling multi-ton stones uphill seems impossible, but ancient engineers develop solutions. They choose routes that minimize steep grades, adding distance to reduce slope. Where hills cannot be avoided, they employ A-frame structures. Tall wooden tripods positioned ahead of the stone have ropes running through blocks at their apex, essentially creating mechanical advantage. Teams pulling ropes that pass through these primitive pulleys can haul loads uphill more easily than by direct pulling. It's still brutally hard work, but physically possible. Descending slopes presents different challenges. The stones cannot be allowed to slide freely, or they'll accelerate out of control, crushing workers and smashing when they hit bottom. Workers use friction and counterweight to control descent. Additional teams on ropes behind the stone create drag, holding it back. Workers may dig trenches behind sledge runners, filling them with branches or earth to create friction. The process is painstakingly slow, but safety demands caution. A runaway 40-ton stone is an unstoppable force that would kill anyone in its path. River crossings require ingenious solutions. The route from Wales to Salisbury Plain crosses multiple rivers. Stones cannot simply be dragged through water, as river bottoms are unstable and currents would sweep stones away. Instead, builders likely use rafts. They construct large platforms using multiple logs lashed together, creating floating platforms capable of supporting stone weight. The stones are carefully rolled onto rafts during low water. Then the rafts are floated downstream or across rivers, guided by teams of workers. Arriving at the far bank, workers beach the rafts and roll stones off onto prepared landing areas. Some scholars believe the Welsh bluestones traveled primarily by water, following coastal routes and rivers for much of the journey from Preseli Hills to Salisbury Plain. This route, though longer in distance, avoids mountains and takes advantage of currents and tides. Prehistoric people in Britain are skilled boat builders, creating wooden vessels capable of coastal navigation. Transporting stones by water is considerably easier than overland hauling. though it requires sophisticated seamanship and carries risks of storms and capsizing. The labor organization required staggers the imagination. Moving one stone from Wales to Salisbury Plain likely takes months. Stonehenge contains about 80 bluestones. If the community moves one stone per year, the bluestone transport alone spans multiple generations. This requires sustained social organization and commitment to a project whose completion the initial planners will never see. Workers need food, housing, and tools throughout the project. Supporting hundreds of workers for extended periods requires agricultural surplus and complex supply logistics. Recent discoveries revealed that Stonehenge construction involves far more than just the stone circle we see today. Excavations uncover a massive landscape of monuments, earthworks, and ceremonial structures surrounding the stone circle. The entire complex represents generations of construction effort, suggesting that Stonehenge is not just a monument but the ceremonial center of a sophisticated civilization that can organize labor on unprecedented scales. Once stones arrive at Stonehenge, they must be shaped and erected. The sarsen stones are shaped using sarsen hammers, stones harder than the sarsens themselves. Workers pound the surface repeatedly, literally hammering away unwanted stone grain by grain. It's exhausting work, taking months per stone. The precision achieved is remarkable. The sarsen lintels feature curved undersides that fit the curve of the upright stones they rest upon. They have mortise and tenon joints, protruding tenons on the uprights, fitting into mortise holes in the lintels, locking them in place. Creating these joints using stone tools requires extraordinary skill and patience. Erecting the upright stones presents yet another challenge. Workers dig pits with sloped sides. They maneuver stones to the pit edge using the same sledge and roller techniques used for transport. The stone is positioned with its base at the pit edge and its top pointing skyward. Workers attach ropes to the top and begin pulling, tilting the stone upward. As it tilts, gravity begins working in their favor. The stone's weight helps pull it downward into the pit. Workers must control this carefully, preventing the stone from falling too fast and cracking. As the stone approaches vertical, they pack the pit with rocks and earth, stabilizing the upright. Adjusting the stone's position requires wooden levers and tremendous effort, shifting the multi-ton mass inch by inch until it stands perfectly vertical. Lifting lintel stones onto the uprights seems impossible without cranes. The lintels weigh up to 10 tons and must be raised 20 feet off the ground. The most likely method involves building wooden platforms, essentially scaffolding, around the uprights. Workers lever the lintel onto a first platform several feet high, then build another platform above and lever the stone up again. Platform by platform, the lintel rises. This method requires immense quantities of timber and weeks of careful work per lintel, but it's physically feasible with Neolithic technology. Once at the correct height, workers slide the lintel sideways onto the uprights, fitting the mortise holes over the tenons. The precision of Stonehenge's construction reveals sophisticated understanding of geometry and astronomy. The monument aligns with the summer solstice sunrise and winter solstice sunset. The heel stone, positioned outside the main circle, marks the precise point where the sun rises on the longest day of the year. Achieving this alignment requires astronomical observations over many years to determine exact solar positions, then careful surveying to orient the monument correctly. The builders understand that they're creating not just a monument but an astronomical instrument, a place where heaven and earth connect through geometry and stone. Stonehenge is not unique. Across Britain and Europe, megalithic monuments demonstrate similar engineering prowess. The Passage Tomb at Newgrange in Ireland, built around 3200 BCE, features a corbelled stone roof that has remained watertight for over 5,000 years. The site aligns so precisely with the winter solstice that sunrise on that day sends a beam of light down the passage to illuminate the inner chamber, a feat requiring understanding of solar mechanics and geometric precision. The standing stones at Carnac in France comprise over 3,000 megaliths arranged in rows stretching for miles. Every one represents transportation and erection challenges similar to Stonehenge. These monuments reveal that Neolithic people possess sophisticated engineering knowledge and complex social organization. They're not primitive savages struggling to survive. They're organized societies capable of monumental projects requiring advanced mathematics, astronomy, and engineering principles. They developed technologies we're only now recreating through experimental archaeology. They coordinate labor on scales that challenge modern project managers. Modern studies using ground-penetrating radar and other technologies continue revealing new aspects of megalithic engineering. Many stone circles include features invisible to casual observation: carefully shaped foundations, drainage systems preventing water accumulation, and earthworks that amplify sound within circles, possibly for ceremonial purposes. The monuments represent cumulative knowledge refined over centuries, each generation learning from predecessors and adding innovations. Every stone standing at Stonehenge represents months of labor by hundreds of people. The complete monument represents work by thousands over generations. These workers aren't compelled by tyranny or slavery. Archaeological evidence suggests they come willingly, perhaps as religious obligations or communal efforts bonding communities together. They receive food and drink during work. Their encampments show evidence of feasting and celebration. Building these monuments is not just labor. It's community affirmation, religious expression, and social bonding on monumental scales. The megalithic monuments standing across Europe testify to human determination and ingenuity. Without modern technology, ancient engineers developed techniques allowing them to move, shape, and erect stones weighing tons. They create monuments that endure millennia, outlasting the civilizations that built them. Every standing stone is a triumph of human capability over physical limitation. These monuments don't require alien intervention or lost technologies. They require human intelligence, determination, and the willingness to dedicate years of effort to projects transcending individual lifetimes. The stones stand today as they stood 4,000 years ago, silent witnesses to humanity's refusal to be constrained by seeming impossibility. Chapter 8: Underground Cities and Water Temples Beneath. The arid landscape of central Turkey lies a world few surface dwellers suspect exists. The city of Derinkuyu stretches downward through solid rock, descending more than 280 feet into the earth through multiple levels of tunnels, rooms, ventilation shafts, and defensive systems. This underground city can shelter 20,000 people for extended periods, complete with living quarters, storage rooms, kitchens, wineries, chapels, schools, and livestock stalls. Walking through its passages today, you enter a feat of ancient engineering that challenges every assumption about the limitations of hand tool excavation. The city wasn't built. It was carved, removed from solid rock, one basket of debris at a time, creating negative space where solid stone once existed. The excavation begins in the volcanic tuff that underlies the Cappadocia region. This rock, formed from consolidated volcanic ash, offers unique properties. It's soft enough to carve with metal tools, but hardens on exposure to air, creating stable walls and ceilings. Yet even relatively soft rock requires immense labor to excavate. Every room, every passage, every shaft represents thousands of hours of chiseling, pounding, and hauling debris to the surface. Archaeological evidence suggests that Derinkuyu's construction spanned centuries, with different civilizations expanding and modifying the underground city over generations. The engineering challenge begins with planning. Unlike surface construction where you build upward from a foundation, underground excavation works downward and outward from initial shafts. Every cubic foot of rock removed must be hauled to the surface. As excavation proceeds deeper, this becomes increasingly difficult. Workers develop systems using buckets hauled up vertical shafts by rope, human chains passing baskets of debris hand to hand, and inclined ramps where debris can be dragged upward on sledges. The logistics of debris removal alone represents a massive engineering and organizational challenge. Ventilation is critical for underground habitation. Without air circulation, carbon dioxide accumulates, oxygen depletes, and the underground city becomes uninhabitable. Hemiunu features a sophisticated ventilation system with shafts descending all the way to the lowest levels. The main ventilation shaft plunges over 180 feet deep, drawing fresh air from the surface and distributing it throughout the city. Secondary shafts provide additional air circulation and emergency exits. The positioning and dimensions of these shafts are random. They're carefully calculated to create natural convection currents. Warm, stale air rises through some shafts, while fresh air descends through others, creating continuous circulation without mechanical fans. Water supply underground seems impossible at first consideration. Hemiunu sits far from rivers or springs. Yet the city includes wells providing fresh water even at the lowest levels. The ancient engineers understand local geology well enough to know that underground water exists at certain depths. They excavate vertical shafts downward until they strike water-bearing layers, essentially creating wells within the underground city. The water likely comes from the same aquifers that feed surface springs in the region. Positioning wells correctly requires understanding hydrogeology, knowing where underground water flows and at what depths it can be accessed. The defensive features demonstrate sophisticated military engineering adapted to underground warfare. At multiple levels, large circular stone doors, weighing up to 1,000 pounds, can be rolled across tunnel entrances from the inside. These doors, several feet thick, block passages completely when closed. Defenders can secure them with wooden bars, creating impenetrable barriers. Attackers cannot roll the doors open because they only roll from one direction. This creates a defense-in-depth system where invaders face multiple barriers as they penetrate deeper. Even if attackers breach one level, defenders retreat behind the next barrier. Narrow tunnels connecting levels serve additional defensive purposes. They're deliberately constructed so only one person can pass at a time. This eliminates attackers' numerical advantages, forcing them into single-file advances where defenders can engage them one-on-one. Some tunnels include murder holes, small shafts connecting to chambers above, through which defenders can drop stones or pour boiling liquids onto attackers below. The entire underground city becomes a three-dimensional battlefield where defenders hold every advantage. The complexity of room layouts reveals sophisticated spatial planning. Living quarters radiate from central passages, maximizing space efficiency while ensuring all rooms connect to main thoroughfares. Communal spaces like dining halls and chapels occupy central locations accessible from multiple levels. Storage rooms sit near living quarters for convenience. Livestock stalls are positioned with access to ventilation shafts to manage odors. The designers understand human needs and social organization, creating spaces that function not just for survival, but for maintaining community life underground for extended periods. The kitchens and food preparation areas include fascinating engineering features. Smoke from cooking fires must be vented to prevent smoke accumulation. The ancient engineers create flue systems connecting kitchen fireplaces to ventilation shafts, drawing smoke upward and out of the city. These flues include baffles and turns that prevent rain from entering while allowing smoke to escape. The hearth designs maximize fuel efficiency, important when wood must be transported underground. Some areas include sophisticated oven designs built directly into rock walls, using the stone's thermal mass to retain heat and cook efficiently. Wine production facilities carved into the rock include press areas, fermentation chambers, and storage rooms. The constant underground temperature around 55 degrees Fahrenheit, provides ideal conditions for wine fermentation and storage. Ancient vintners carved troughs into the rock where grapes are crushed. The juice flows through carved channels into fermentation vessels. The wine is then stored in large ceramic amphorae placed in carved niches. The entire process occurs underground, with grapes being the only material that needs to be brought down from surface vineyards. The engineering knowledge required to excavate Hemiunu safely is considerable. Rock properties must be understood. Ceiling spans cannot exceed what the rock can support without collapsing. Load-bearing walls must be left in strategic positions. Some areas feature carved pillars, rock left in place while surrounding material is removed, creating columns that support ceilings of larger chambers. The thickness of these pillars is calculated, consciously or through experience, to support the weight above them. Too thin, and they'll crush under the load. Too thick, and valuable space is wasted. Water management isn't limited to supply. Drainage systems must handle water accumulation from wells, cooking, and condensation. The floors of passages and rooms are shaped with slight slopes, invisible to casual observation, but sufficient to drain water toward collection points. Retry A. Continue carved channels in the floor guide water flow. At collection points, water either drains into sumps that can be bailed out periodically or flows into deeper wells that act as drainage sumps. This prevents flooding that would make lower levels uninhabitable. The engineers understand that water naturally seeks lower levels and design the city's hydrology to manage this reality. Lighting underground presents challenges that modern people, accustomed to electric illumination, barely consider. Oil lamps provide the primary light source. The lamps consume oxygen and produce smoke, adding to ventilation requirements. The ancient designers position lamp niches in walls at strategic locations, providing light where needed while minimizing fuel consumption. Polished surfaces on some walls may serve to reflect and amplify available light. In critical areas, multiple lamps ensure adequate illumination. The residents live in semi-darkness much of the time, their eyes adapting to light levels that would seem impossibly dim to us. Across the ancient world, similar underground engineering marvels demonstrate human ingenuity in working with negative space. The rock-hewn churches of Lalibela in Ethiopia, carved from solid rock in the 12th and 13th century CE, represent perhaps the ultimate expression of subtractive architecture. Unlike the Hemiunu, which is excavated downward into the earth, Lalibela's churches are carved from above, workers removing rock around the intended structure until freestanding buildings emerge from the bedrock. The Church of St. George, the most famous, sits in a cross-shaped pit carved 40 feet deep. The church itself, perfectly shaped with walls, windows, doors, and interior spaces, has been carved from a single massive piece of rock. Not a single stone has been laid. Everything is subtraction, removal, carving away the unnecessary to reveal the sacred form hidden within stone. The engineering precision required for Lalibela's churches astounds modern observers. Workers begin by carving trenches around the perimeter of the intended structure. They work downward, gradually exposing the top of what will become the roof. As the trenches deepen, the rough form of the building emerges. Workers then carve windows and doors from the outside, gradually hollowing the interior. They must constantly ensure that walls remain thick enough to support the roof, that pillars are positioned correctly to bear loads, that the entire structure remains monolithic with the bedrock beneath. One major mistake could crack the rock, potentially destroying years of work. There are no second chances, no opportunities to add material back if too much is removed. The interiors of Lalibela's churches feature carved columns, arched ceilings, and decorative elements that mimic constructed buildings but are entirely carved from living rock. Walking inside, you might think yourself in a stone building until you realize that the walls, floor, ceiling, columns, and all decorative elements are continuous, carved from a single mass of stone. The churches include functioning features like drain holes in floors, directing water out of the structure, carved gutters on roofs preventing water accumulation, and ventilation openings ensuring air circulation. Water temples in ancient Bali represent another form of sophisticated underground engineering. These temples, called pura, serve as focal points for the Subak system, a UNESCO-recognized traditional irrigation management system. The temples sit at strategic locations in the watershed, with underground tunnels and chambers connecting to natural springs and aquifer access points. Ancient Balinese engineers understand hydrology with precision, knowing where water naturally accumulates underground and how to access it efficiently. The Mother Temple of Tirta Empul, built around a sacred spring in 960 CE, demonstrates sophisticated hydraulic engineering combined with spiritual purpose. The spring emerges from underground through carved stone channels into purification pools where devotees bathe in sacred water. The flow rate remains constant year-round, suggesting the spring taps a stable aquifer. The pools are designed with calculated dimensions, ensuring proper water circulation. Fresh spring water enters continuously, while used water overflows into drainage channels, maintaining the pool's purity. The hydraulic engineering serves religious purposes while demonstrating deep understanding of groundwater hydrology and fluid dynamics. The underground tunnels connecting water temples across Bali's landscape form networks controlling water distribution across entire watersheds. These tunnels, some dating back over 1,000 years, channel spring water from highland sources to lower elevation rice terraces. The tunnels maintain precise gradients, ensuring water flows continuously without excessive velocity that would cause erosion. Where tunnels emerge to the surface, they feed into distribution systems that allocate water to specific rice terraces according to traditional agreements between farming communities. The qanats of ancient Persia represent perhaps the most extensive underground water management system ever created. These gently sloping tunnels tap into aquifers in highland areas and carry water by gravity flow for many miles to settlements in arid lowlands. Some qanat systems stretch over 30 miles. The tunnels must maintain precise gradients, typically 1 to 3 feet of drop per 1,000 feet of horizontal distance, just enough to ensure flow without creating excessive velocity. Too steep and water erodes the tunnel. Too shallow and silt accumulates, blocking flow. Qanat construction begins with locating aquifers in foothill regions where mountain water seeps into underground layers. Workers sink a vertical shaft called a mother well until they reach water-bearing layers. From the bottom of this shaft, they begin excavating horizontally, creating a tunnel that slopes very gently downward in the direction of the settlement to be served. As excavation proceeds, workers sink additional vertical shafts at intervals of about 100 feet. These shafts serve multiple purposes. They provide access for removing excavated material, they supply ventilation for workers, and they allow light to reach workers in the tunnel below. The vertical shafts create a distinctive landscape feature visible from space in regions with extensive qanat systems. Lines of circular wells march across landscapes, marking underground tunnels beneath. Each shaft requires careful positioning to maintain the precise tunnel gradient. Workers use simple but effective leveling instruments and careful surveying to ensure each shaft connects properly to the main tunnel at the correct depth. The mathematical and surveying challenges are considerable, especially when tunnels stretch for miles through variable terrain. Underground excavation in qanats requires extraordinary courage. Workers descend vertical shafts using rope and bucket systems, then excavate horizontally in darkness, working by oil lamplight. The constant risk of cave-ins makes this among history's most dangerous occupations. Yet qanat systems proliferate throughout Persia, Central Asia, and North Africa because they provide reliable water in arid regions. A properly constructed canal can function for centuries with minimal maintenance, delivering steady water flow year-round. The social organization required to build and maintain these underground water systems demonstrates sophisticated governance and cooperation. Canal construction requires years of labor by skilled workers. Maintenance requires ongoing vigilance, with workers periodically descending shafts to clear silt accumulation and repair damage. Communities develop elaborate legal frameworks governing water rights, allocating shares of canal water according to traditional formulas that balance equity with investment in construction and maintenance. The ingenuity of ancient underground engineering extends to waste management. In ancient Rome, the Cloaca Maxima, one of the world's earliest sewage systems, channels waste through underground tunnels into the Tiber River. These tunnels, large enough for workers to enter for maintenance, are constructed with precisely shaped stone and concrete. The tunnels maintain gradients ensuring waste flows continuously without accumulating. Ventilation shafts provide air circulation and access points. The system demonstrates that ancient engineers don't just bring fresh water into cities, but also remove waste, understanding that urban health depends on both supply and sanitation. The underground cisterns of Constantinople, built to ensure water supply during sieges, showcase engineering on a massive scale. The Basilica cistern, completed in 542 CE, stretches nearly 500 feet long and 230 feet wide, with a vaulted ceiling supported by 336 marble columns arranged in 12 rows. The cistern can hold about 21 million gallons of water. Workers excavate the massive chamber from soft earth and limestone, then construct the elaborate column and vault system to prevent collapse. The cistern connects to city aqueducts through underground channels, filling when water is plentiful and providing reserve supply during droughts or sieges. The engineering ensures water remains fresh through circulation and preventing sunlight from entering, which would promote algae growth. These underground engineering marvels share common principles despite spanning different cultures and purposes. They all require understanding geology, knowing what rock can be excavated safely and what will remain stable as roof or wall. They demand sophisticated surveying and mathematical skills to maintain proper gradients, alignments, and dimensions. They need careful planning before excavation begins, as mistakes underground are difficult or impossible to correct. They require extraordinary labor organization, as underground work is slow, dangerous, and requires specialized skills. Most of all, they demonstrate that ancient engineers understand three-dimensional space with sophistication matching modern practitioners. Modern explorers using laser scanning and photogrammetry continue mapping these ancient underground structures, revealing complexities previously unknown. The scans show that many underground spaces connect in ways not obvious to visitors walking through them. They reveal engineering features like expansion joints, load-bearing principles, and hydraulic calculations that demonstrate advanced knowledge. Each discovery reinforces that ancient underground engineers aren't stumbling in darkness. They're working with clear understanding of principles, refined techniques, and bold vision that doesn't accept surface limitations as final constraints. Where the surface world presents obstacles, they simply go under, through, or around, creating entire civilizations beneath the earth. Chapter 9. Seismology. The ground began to shake violently in ancient Japan, 735 CE. The timber-framed temple of Horyuji trembles as seismic waves pulse through the earth, a powerful earthquake that collapses stone buildings throughout the region. Workers and monks flee into open courtyards, watching in terror as the 5-story pagoda sways dramatically, leaning first one direction then the other, its roof ornaments tracing wide arcs through the air. The shaking continues for what feels like eternity, but is actually less than a minute. When stillness returns, the monks cautiously approach the pagoda, expecting to find it collapsed or at least severely damaged. Instead, they find it standing perfectly intact, not a beam broken, not a joint failed. The pagoda has danced with the earthquake and survived. 13 centuries later, it still stands, having weathered countless earthquakes, remaining the world's oldest surviving wooden building. The secret to Horiuji's survival lies not in rigidity, but in flexibility, a profound engineering insight that ancient Japanese and Chinese builders developed through bitter experience with frequent earthquakes. Stone buildings, which work well in seismically quiet Europe, crack and collapse when earthquake waves cause different parts of a structure to move in different directions simultaneously. Stone's strength and compression becomes a fatal weakness in earthquakes. It cannot flex, cannot bend, cannot absorb seismic energy. When stress exceeds stone's limits, it fractures catastrophically. Wood behaves entirely differently. It's strong in both compression and tension. It can flex significantly without breaking. Wooden joints can slide and absorb movement. Ancient Asian builders developed construction techniques that exploit these properties brilliantly. The pagoda at Horiuji uses a post and beam frame construction, where vertical columns support horizontal beams. The joints connecting these elements aren't rigidly fixed with nails or bolts. Instead, they use sophisticated joinery techniques where wooden elements interlock through precisely cut shapes. Mortise and tenon joints, dovetails, and complex interlocking systems hold the structure together while allowing limited movement. The central pillar of the pagoda demonstrates engineering genius. Called a shinbashira, this massive timber extends from foundation to near the top of the structure, but isn't rigidly connected to the floors or roof. It hangs suspended, supported at the bottom, but free to move independently of the surrounding structure. During an earthquake, the building sways in response to ground motion. The massive central pillar, however, acts as a pendulum, swinging with different frequency and phase than the building around it. This creates a counterweight effect, the pillar's movement damping the building's oscillations. It's a tuned mass damper, the same principle modern engineers use in skyscrapers, developed over 1,000 years earlier through empirical observation and refinement. The pagoda's construction includes numerous other seismic-resistant features. Each story is structurally independent, connected to stories above and below, but capable of moving somewhat independently. During an earthquake, upper stories might move more than lower ones, but the independent construction prevents these differential movements from tearing the structure apart. The roof design, with its characteristic upturned eaves extending far beyond the walls, serves aesthetic purposes, but also structural ones. The heavy roof mass helps stabilize the structure while the extended eaves distribute weight away from walls, reducing stress concentration. The foundation system in ancient Japanese temple construction demonstrates sophisticated understanding of soil mechanics and seismic response. Rather than deep, rigid foundations that might crack during ground shaking, temples often sit on relatively shallow foundations that can slide somewhat during earthquakes. This seems counterintuitive. Wouldn't sliding damage the building? In practice, allowing controlled sliding at the foundation dissipates seismic energy that would otherwise tear through the superstructure. The building moves with the ground rather than fighting it, surviving through flexibility and motion rather than rigid resistance. The bracket systems supporting roof eaves in traditional Asian architecture are marvels of structural engineering disguised as decoration. These brackets, called dugong in Chinese architecture, consist of interlocking wooden brackets stacking outward from the tops of columns, each layer projecting further than the one below. The brackets distribute roof weight across multiple columns while creating a springy, flexible support system. During earthquakes, the brackets compress and rebound, absorbing energy like shock absorbers. The complex friction between interlocking wooden elements dissipates energy that would otherwise damage structural members. Ancient builders in earthquake-prone regions developed these techniques through observation and experimentation spanning centuries. Buildings that survive earthquakes inform future construction. Techniques used in failed buildings are abandoned or modified. This evolutionary process creates building traditions remarkably effective at earthquake resistance without any understanding of modern seismology or structural dynamics. The builders don't know about frequency response, resonance, or wave mechanics in the modern sense, but they understand empirically that flexibility, weight distribution, and careful joinery create buildings that survive when the earth moves. The Great Wall of China, often thought of purely as a military structure, incorporates sophisticated seismic-resistant design. In earthquake-prone regions, sections of the wall use construction techniques that allow movement without collapse. Some sections employ a core of rammed earth faced with brick or stone. This composite construction combines the compression strength of stone with the flexibility of earth. When seismic waves pass through, the earth core can deform and absorb energy, while the stone facing protects the core from erosion. Joints between stone-facing blocks are sometimes filled with flexible materials like rice mortar, a mixture that can accommodate small movements without cracking. Rice mortar itself represents an ancient engineering material of remarkable properties. Chinese builders discover that adding sticky rice paste to lime mortar creates a composite material stronger and more flexible than either component alone. The organic compounds from the rice create a matrix that binds the inorganic lime and aggregate into a material that can flex without cracking. Chemical analysis reveals that the rice creates an organic-inorganic composite at the molecular level, similar in principle to modern polymer-modified cements. This material helps mortar joints survive earthquake movements that would crack pure lime mortar. In ancient Peru, the Inca developed entirely different seismic-resistant building techniques adapted to their stone building tradition and local geology. Inca masonry at sites like Machu Picchu and Sacsayhuaman features massive irregular stones fitted together with extraordinary precision. The stones aren't rectangular blocks, but complex three-dimensional puzzle pieces, each shaped to interlock with neighbors. The stones lack mortar, sitting together through gravity and friction alone. This seems like a recipe for collapse during earthquakes. Instead, it's brilliantly earthquake-resistant. When seismic waves shake the structure, stones can shift slightly, moving against each other, then settling back into place when shaking stops. The walls dance during earthquakes, moving without collapsing. The technique, called ashlar masonry, requires extraordinary stone-cutting skill. Each stone must be shaped to fit perfectly against all adjacent stones. Workers likely create each stone shape through iterative fitting, placing a rough stone, marking contact points, removing it for shaping, replacing it, marking again, and repeating until the fit is perfect. The largest stones weigh over 100 tons, and fitting them requires moving them multiple times during the shaping process. The labor investment is enormous, but the result is structures that have survived centuries in one of Earth's most seismically active regions. The Inca also employed trapezoidal architecture, where doorways, windows, and niches taper inward toward the top. This shape is inherently stable, with the widest part at the base supporting narrower sections above. During earthquakes, the trapezoidal shape helps structures resist collapse. Even if stones shift, the geometry tends to resettle into stable configurations. Modern engineers analyzing Inca structures recognize sophisticated understanding of stability and earthquake resistance encoded in forms that appear purely aesthetic. In ancient Greece and Rome, despite less frequent earthquakes than in Asia or the Pacific Rim, builders developed techniques for earthquake resistance. The Parthenon in Athens, though much damaged by human conflict and weathering, survives numerous earthquakes over 2,500 years. The temple's design incorporates subtle flexibility through carefully designed joints. The marble blocks are connected with iron clamps set in lead. The lead allows slight movement while the iron provides strength. This creates joints that can accommodate small movements without cracking the marble. The step foundation distributes weight evenly and can settle slightly without destabilizing the structure. The Romans developed concrete construction, partly to address limitations of stone in earthquake-prone Italy. Concrete, as monolithic nature, means structures move as units rather than assemblies of separate stones that can separate during shaking. The Romans don't fully understand seismology in the modern sense, but they observed that concrete buildings often survive earthquakes better than comparable stone structures. The Pantheon, as massive concrete dome, has survived numerous moderate earthquakes over 18 centuries, partly because it is a single, unified structure rather than an assembly of individual elements. The ancient builders' approach to seismic design differs fundamentally from modern practice in one crucial aspect. They design for survival, not for prevention of damage. Modern seismic codes aim to keep buildings usable after earthquakes. Ancient builders accept that buildings might be damaged but must not collapse catastrophically. This philosophy leads to designs that might need repairs after major earthquakes but won't kill occupants through sudden collapse. Flexible joints might need reseating. Cracked walls might need patching, but the overall structure remains intact. Archaeological evidence reveals that ancient builders are aware of side effects on earthquake damage. They observe that buildings on solid rock generally fare better than those on soft soil. They notice that structures in valleys sometimes suffer more damage than those on hillsides. Modern seismology explains these observations through concepts like soil amplification and basin effects, but ancient builders don't need these explanations. Empirical observation tells them where to build and where to avoid, knowledge encoded in traditional practices and taboos. Some ancient cultures develop earthquake prediction methods, though effectiveness varies greatly. Chinese records from the Han Dynasty describe a device called a seismoscope, invented by Zhang Heng in 132 CE. The device consists of a large bronze vessel with 8 dragon heads around its circumference, each holding a bronze ball. Inside sits a pendulum mechanism. During an earthquake, the pendulum swings, triggering a mechanism that releases a ball from the dragon's mouth in the direction of the earthquake. While this device cannot predict earthquakes, it can detect them and indicate their direction, potentially useful for knowing where to send aid in a large empire with slow communications. The sophisticated earthquake resistance of ancient buildings becomes apparent through their longevity. The Haryuji Pagoda stands for over 1,300 years in a region experiencing frequent earthquakes. Inca stonework survives centuries, while Spanish colonial buildings constructed with European techniques collapse in subsequent earthquakes. The Parthenon endures 2,500 years. These structures survive not through luck, but through engineering principles refined over generations. Each earthquake that doesn't destroy a well-built structure validates its design. Each collapse teaches lessons incorporated into future construction. Modern seismic engineers studying ancient earthquake-resistant structures gain insights applicable to contemporary design. The principle of base isolation, now used in modern seismic design, appears in ancient Japanese temples. Energy dissipation through friction in joints, a modern seismic design strategy, is fundamental to traditional timber frame construction. The concept of rocking foundations that dissipate energy through controlled movement emerges in ancient practice. These aren't coincidences. Ancient builders discover through experience the same physical principles modern engineers derive through mathematical analysis. The ancient architecture of flexibility represents triumph of empirical knowledge over theoretical limitations. Without understanding wave mechanics, resonance frequencies, or structural dynamics equations, ancient builders create structures that perform as well as or better than modern engineered buildings in earthquakes. They achieve this through careful observation, intergenerational knowledge transmission, willingness to learn from failures, and deep intuitive understanding of how buildings and earth interact. Every ancient structure still standing in earthquake zones testifies that you do need to understand why something works to make it work brilliantly. You need keen observation, patient refinement, and respect for accumulated wisdom. The flexibility of ancient earthquake-resistant architecture is more than structural. It's intellectual flexibility, willingness to adapt practices to local conditions, to learn from experience, and to value survival over rigid adherence to imported building traditions that don't match local realities. Chapter 10. The Mathematics of Beauty and Perfect Proportion. The sculptor Polykleitos stands in his workshop in ancient Argos, 450 BCE, contemplating a half-finished bronze statue. Before him rests his treatise, the Canon, a mathematical text describing ideal human proportions. But Polykleitos isn't merely recording measurements. He's encoding a profound insight. Beauty is not subjective preference, but mathematical relationship. And the same proportions that create aesthetically pleasing art also create structurally sound architecture. This fusion of mathematics, aesthetics, and engineering defines ancient approaches to monumental construction, where temples aren't just buildings, but three-dimensional demonstrations of cosmic harmony. The Greek concept of symmetria doesn't mean symmetry as we understand it today, where a left mirrors right. Instead, it means proportion, the relationship of parts to whole and parts to each other. The Parthenon embodies this principle completely. The temple's dimensions relate through precise ratios. Column heights relate to diameters through specific formulas. The spacing between columns follows carefully calculated patterns. Wider at corners to compensate for the optical illusion, the corner columns appear thinner when silhouetted against sky. Every dimension connects mathematically to every other dimension, creating unity through numerical relationship. The architects Iktinos and Kallikrates, designing the Parthenon under sculptor Phidias's artistic direction, employ mathematical principles that seem to anticipate discoveries of Renaissance mathematicians. The golden ratio, approximately 1.618, appears throughout the structure's proportions. These relationships aren't accidental. Greek architects study geometry intensively, understanding that certain proportions create visual harmony while others feel awkward or unstable. But the Parthenon incorporates something even more sophisticated: deliberate departures from mathematical perfection to account for human perception. The temple has almost no truly straight lines. The platform curves upwards slightly in the middle, rising about 4 inches over its 228-foot length. Without this curvature, the platform would appear to sag in the middle due to optical illusion. The columns lean inward slightly rather than standing perfectly vertical. The corner columns are slightly thicker than interior columns and spaced closer to their neighbors, counteracting the slimming effect of being viewed against bright sky. These refinements, called entasis, demonstrate that Greek architects understand perception as well as mathematics. They know that mathematical perfection doesn't produce perceived perfection. The human eye and brain interpret visual information through complex processes that create optical illusions. The architects mathematically calculate how to compensate for these illusions, creating a building that appears perfect even though its actual geometry deviates deliberately from perfection. It's engineering serving aesthetics through sophisticated understanding of human psychology. The column design itself balances structural necessity with aesthetic proportion. Greek columns generally follow one of 3 orders: Doric, Ionic, or Corinthian, each with different proportional systems. Doric columns, like those of the Parthenon, are relatively stout, with height about 5 to 6 times their base diameter. This ratio isn't arbitrary. It provides adequate strength to support roof weight while appearing appropriately robust for a temple dedicated to a powerful deity. Ionic columns are more slender, about 9 times their diameter in height, creating a more delicate aesthetic suitable for smaller temples or interior colonnades. These proportional systems aren't merely aesthetic preferences. They encode structural understanding. A column too slender for its height risks buckling under load. A column too thick wastes material and creates a heavy, oppressive appearance. The orders represent optimized solutions, balancing structural requirements with aesthetic goals. Greek architects developed these systems through generations of experience, refinement through trial and error, and theoretical analysis exploring mathematical relationships. The Romans adopt and adapt Greek proportional systems, as documented in Vitruvius's De Architectura, written around 15 BCE. Vitruvius describes ideal proportions for temples, forums, basilicas, and private houses. He relates building proportions to human body proportions, arguing that just as the human body follows harmonious mathematical relationships, so should architecture. Roman engineers apply these proportional principles to utilitarian structures with stunning aesthetic results. The Pont du Gard aqueduct in southern France demonstrates how structural necessity and aesthetic proportion combine. The bridge's 3 tiers of arches diminish in size as they ascend, with the tallest arches at the bottom, medium arches in the middle tier, and smallest arches carrying the water channel at the top. This arrangement makes structural sense, with the heaviest load supported by the largest arches. But it also creates visual harmony, the diminishing scale creating a sense of upward movement and lightness despite the bridge's massive stone construction. The arch proportions themselves follow careful mathematical relationships. Each arch's rise relates to its span through ratios that balance structural efficiency with aesthetic appeal. Too shallow an arch appears weak and creates high lateral forces on supports. Too steep an arch appears awkward and doesn't span efficiently. The Romans find optimal ratios, typically with the rise about half the span for semicircular arches. These proportions appear repeatedly in Roman construction, from aqueducts to amphitheaters to triumphal arches. In ancient Egypt, proportional systems governed temple and pyramid design with obsessive precision. The Great Pyramid's base-to-height ratio approximates the mathematical constant pi. Whether by design or remarkable coincidence remains debated. Egyptian architects use a grid system for temple design, overlaying proposed building layouts with squares subdivided into smaller units. Building elements align with grid lines, ensuring proportional relationships remain consistent throughout construction. This approach ensures that buildings feel unified, with every element connected mathematically to every other element. The Hindu temple architecture of ancient India incorporates sophisticated mathematical and geometric principles in structures called Vastu Shastra. These temples follow mandala patterns, geometric diagrams representing cosmic order. The temple plan is typically square, divided into grid patterns with sacred proportions. The central sanctum sits at the mandala's center, representing the axis mundi connecting earth and heaven. The temple towers rise in diminishing tiers following precise geometric progressions, each level smaller than the one below according to specific ratios. The Khmer temples of Angkor in Cambodia represent perhaps the ultimate expression of sacred geometry in architecture. Angkor Wat, built in the 12th century CE, is designed as a microcosm of the Hindu universe. The temple's 5 towers represent Mount Meru, the sacred mountain at the center of Hindu and Buddhist cosmology. The dimensions encode astronomical and calendar cycles. The temple's layout incorporates equinox alignments, with the sun rising directly behind the central tower on equinox mornings when viewed from the western entrance. Every dimension carries symbolic and mathematical significance. The ancient engineer's story is ultimately humanity's story, a narrative of problem-solving, innovation, and the relentless drive to transform ambitious visions into physical reality. From the mathematically perfect pyramids of Egypt to the earthquake-dancing pagodas of Japan, from Roman aqueducts carrying water through mountains to Inca stonework defying seismic destruction, Ancient engineers prove that human ingenuity knows no era, no limitation that cannot be overcome through knowledge, determination, and skill. These weren't primitive people stumbling toward understanding. They were sophisticated scientists working within different technological constraints, developing solutions we're only now beginning to fully appreciate. Their mathematics was rigorous, their material science sophisticated, their structural understanding profound. They commanded projects requiring coordination of thousands, solved problems that would challenge modern engineers, and created monuments outlasting the civilizations that built them by millennia. The questions we asked at the beginning of this journey, how did they do it, have answers that humble us. They did it through centuries of accumulated knowledge, through master-apprentice transmission systems, preserving and refining techniques across generations. They did it through empirical observation, learning from successes and failures, developing intuitive understanding that matched or exceeded what formal analysis might provide. They did it through social organization, mobilizing entire societies towards shared goals. Most of all, they did it through refusing to accept limitations as final, viewing obstacles as problems awaiting solutions. The relevance of ancient engineering extends far beyond historical curiosity. As modern society faces challenges of sustainable building, earthquake-resistant construction, water management in arid regions, and creating durable infrastructure, ancient solutions offer proven techniques developed and refined over centuries. Roman concrete lasting 2 millennia suggests alternatives to modern materials degrading within decades. Japanese flexible timber construction provides earthquake resistance lessons applicable to contemporary seismic design. Ancient passive heating and cooling techniques offer low-energy alternatives to mechanical climate control. The ancient engineer's legacy isn't just historical. It's practical knowledge applicable to present challenges. Perhaps most important, ancient engineering reminds us what humans can achieve when we combine intelligence with determination. Every massive stone moved without machinery, every mountain tunneled through with hand tools, every mathematically perfect structure raised without computers demonstrates that human capability extends far beyond what we imagine possible. The ancient builders didn't have our advantages, but they had something equally powerful: unwillingness to accept impossibility. The monuments they created will outlast our lifetimes as they've outlasted countless generations before us. When we stand before the Great Pyramid or walk through the Pantheon, we're not just observing ancient buildings. We're experiencing dialogues across time, where ancient engineers speak to us through their work, reminding us that excellence endures, that what's built well serves not just its moment, but eternity. Their greatest engineering achievement isn't any single structure, but the proof they provide that human intelligence, skill, and determination can transform dreams into stone reality that will inspire and challenge humanity for thousands of years to come.